Hello, my lovers. Paper 1 from 2018 today. Let's get going. So first one we've got some integral. We're going to integrate this from 1 to 4. So when it's like this, there's nothing weird on the bottom, as in there's no pluses or minuses, it's just a single term. Just divide them all off. So we've got 3 over x root x. So that'd be 3 times by x to the power of minus 3 on 2. Take away 2. This x will cancel with that one. So 1 over root x, x to the minus half. We want to integrate that still from 4 to 1. So doing that, let's raise the power there. We'll get a negative half and divide this by negative half. So times it by negative 2, we get negative 6. Similar to on the right, we'll raise that up to 1 half. Dividing 2 by a half gives us 4, and we'll retain the negative. And we want to plug in the values of 4 and 1. So doing 4, what we're going to get, root 4 is 2. 6 over 2 is 3, but that's negative. Again, root 4 is 2, times by 4 is an 8. We've got a 1, so that's going to be a minus 6, minus 4. So altogether, minus 10. But obviously, that thing, we're taking that away. So combine these bits, minus 11. Combine that bit, plus 10. Altogether, then, we should have negative 1. Is that the right answer? It is indeed. Number 2, then. We have an arithmetic progression. Has a first term a, common difference d. The sum of the first 5 is equal to the sum of the first 8. Which of the following expressions represent a and d? Okay, sum of the first 5, what do we get from that? Will be n over 2, i.e. 5 over 2. All times by 2 times a, plus n minus 1, i.e. 4, times by d. Similar thing on the right then, 8 over 2 is 4. 2a, which is the last time. n minus 1 will be 7. So 7 lots of d in there. And now let's just expand everything out. This 2 can be useful, so half of 2 is obviously 1. Times by the 5 is a 5. Similar thing here, 2 goes with that to make a 2. Times by 5 is a 10. On the right, we'll have 8a plus 28d. Let's take some things away. We'll have 18d on the right here. 18, that's not 18. And we can have also 3a on the right, but we'll make it a 3 on the left. And you can see here the d's are going to be negative, so we'll leave the negative with this one. Divided by 3, a should be minus 6 lots of d, which is answer C, which is correct. On to number 3 then. Find the shortest distance between these two circles. Whenever you've got this, find the difference between the centres and then subtract both radii from it. So imagine wherever they are, you can have one circle there, one over there. You just want to find that difference, so that distance, but taking away the two little ones that you've got, like in there and in there. So exactly that, the distance between the two centres, and then subtract the two radii from both. So let's do that. What we're going to get, well, one centre here is at minus 2, 3. This one is at 7 and minus 6. So difference in both of those, we have a 9 and a 9. Okay, so the actual magnitude of this then, that's not what we're doing. We want to do magnitude of that, take away that. And so I think, yeah, magnitude of this thing, what we're going to get is 9 root 2. Looking at the radii from these, this is obviously going to be there for r is root 2 on the bottom. Here, similar sort of idea, but this is 9 times 2 in it, so it's going to be 3 root 2 for that one. So altogether, we've got 9 root 2, take away 3 root 2, take away root 2, gives us 5 root 2 at the end. Is that correct? Answer is E. Yep, lovely jubbly. So number 4 then, we have some quadratic looking thing, not quite a quadratic, and some straight line. Let's rearrange the straight line, plug it into this one, because we want to find what values of A do we have two distinct real solutions. So in this case, we can say that y is equal to a minus x, and just go and plug all that stuff in there. So we're going to have 3x squared plus 2x times this, so 2ax minus 2x squared, and that will all equal to 4. So making this into a quadratic then, we're going to have x squared plus 2ax minus 4 equals 0. So discriminant of that thing, what we're going to have is b squared, i.e. 4a squared. It's going to be 2a all squared, so 4a squared, Take away 4 times by a, which is going to be 1, and then times by c, i.e. the minus 4. So make that minus 4 into a positive 16. And that's good. And we want the question then, when is this thing always positive? Well, it's always positive. This is strictly greater than 0 for all a's. All real values of a anyway. Yeah, for all real values of a. Looking at this, no value you can put in. If you square it, it's going to be positive, and adding on 16 is up in there. We'll make it even bigger. So that looks all good. Every single value for a should have 2 distinct real solutions. On to number 5 then. We've got some cubic. A, B, and C take the values 1, 2, and 3, with no 2 of them being equal, and not necessarily in that order. The remainder when f is divided by x plus 2 is r, and x plus 3 is going to be s. What's the largest possible value for r minus s? So doing this, we can say a few things, like when we plug in the value for A, B, and C take the values of these. Okay, when we plug in minus 2, what are we going to get? We'll get minus 8. We will then get a plus 4a minus 2b plus a c, and that should equal to r. And then very similarly, we're going to have minus 27. It's going to be plus 9 lots of a minus 3 lots of b plus a c should give us s. We want r minus s, yeah? So let's do top row, take bottom row. So r minus s, then what we're going to get? Well, minus 8 take away minus 27, so it's like plus 27, and it take away 8, so it gives us a 19. And how many a's will we have? Top take away bottom, we'll have minus 5. How many b's will we have? Top take away bottom, so it's going to be, well, this would be a positive 3, wouldn't it? Take away 2 is going to be 1. And the c's will go. So this is good. Let's think about the biggest value we can get from this then. So a, b, and c must be 1, 2, and 3. Can't be the same, none of them being equal. And don't have to be in that order, can't be in any order. So we want this number to be as big as possible. So ideally, what we'd like to do is take away the least and add on the most. So if we make a be 1, we take away 5, we're at 14. Make b be 3, the biggest it could be. We'll add back up to 17 again. And that is the answer. Yeah, D. Lovely, jubbly. Right, number 6 then. Whenever you're looking, so we want to find the number of solutions to this stuff. Whenever you've got things like this where we have trig and non-trig together, separate the variables, but separate the functions. So we'll leave, we'll make a tan. So sine over cos will give us a tan 2x. And I'll bring that x to the other side as 1 over x. And now all we're going to do is plot them both. So we'll go and draw tan 2x, we'll go and draw 1 over x. So tan 2x, we should have this sort of stuff, shouldn't we? Goes through. We should figure out how many of those we're going to get. I think that's all good though. So in general, we would be 180 wide. Or we'd be pi wide. But this being tan, being 2x in, sorry, we get twice as many happen in that thing. So instead of it being there's 4, no, sorry, instead of there being 2 in that, there should be 4. And you can see here then I've got 1, 2, 3, 4, but this one's only a half, so I would have the other bottom like that as well, where this then should be exactly the bits we need. And the next thing then, let's just go through and draw the 1 over x. Well, it's going to do something like this, and how exactly it does it, who cares? What the only thing we actually do care about is that, and that. And you can see therefore it's going to be 4. That looks good. On to number 7. The non-zero constant k is chosen so that the coefficients of x to the 6 in these expansions are equal. What's the value of k? Okay, so it's going to be the third thing from there. Do you know what I mean? So we've got x squared inside. To make x 6, you need to have 3 of those combined together. So from the first one, we're going to have 7 choose 3 times by, you would have 1 to the 4. Yep, lovely. And then it's going to be the other stuff to the 3. So k cubed. And this needs to equal then, similar idea on the other side, but 10 choose 6. And from there, what's going to go on, we would have the same idea, but this k will have a 4 onto it. And the x would have a 6. So what's the value of k? We can see here we've got k cubed. Here's k to the 4. Let's divide by a k, therefore. So k should be 7 choose 3 over 10 choose 6. 10 choose 6 is the same as 10 choose 4, but it does make a huge difference here. Because what I'm going to do now is figure out them both using their actual formulas, do you know what I mean? So let's do it maybe as 2 fractions. We'll have 7 factorial over 3 factorial times by 4 factorial. And then for the 10 choose 6, I'll do the same but upside down. So 10 factorial, 4 factorial, 6 factorial. So let's cancel some bits. 4 factorial can go with 4 factorial. We can cross out to like the 7 and this 10 and leave just like 10 times 9 times 8 on the bottom. So that's those bits gone. And then similar with the 6, what we're going to do is make that 654 on the top and having the 3's go away with the other bits. This looks good. What can we do from here? Well, 5 over 10 is 1/2. 4 over 8 is 1/2. 6 over 3 is 2/3. I can get rid of a 2 and a 2. I'm left with 1 over 6, which is A. Is that the right one? Let's have a look. 7. Well, the last one was 4, wasn't it? Yeah, the last one's 4. That's good. And this one should be A, 1/6. Yep, that'd be lovely. Oh, it looks good. So what we've got now, the sum to infinity of a geometric progression is 6. The sum to infinity of the squares of each term in the progression is 12. Find the sum of the cubes. Okay. So what we're told then, we have a plus ar squared plus ar cubed. No, what we're doing, we've got too many powers there. Go down 1 power. All the way through like that is going to be 6. So we can write then as a over 1 minus r is equal to 6. On the next one, the sum of the squares. If we think what the square of each of these terms is, we have a squared, and then a squared r squared. And then we're going to have a squared r to the 4, etc., etc. So we can get another formula. The first term is a squared, and we're timesing by r squared every time. And that gives us a 12. So very similar formula. We just want to figure out then what is a, what is r. Simultaneous equations, just a little bit fancy version of it. But what we can do, let's make everything into kind of one row of things, you know what I mean? So 6 lots of 1 minus r there. And here we have the a squared is going to be 12 times 1 minus r squared. And this thing, what we can do, that right-hand side, let's separate that out a little bit. So we'll still have a squared on the left. The 12 we can break up into a 2. And then that bracket can be 1 plus r. And then obviously we're going to have the 6 to make the 12. And the 1 minus r for the other bit of the bracket. This is that bit. So this is equal to a. So what we're able to do, bring that to the other side, we'll have a squared minus 2, lots of 1 plus r, lots of a, equal to 0. So either a is 0. If a is 0, it's not a very exciting thing. It's everything's 0. Do you know what I mean? I don't think it's even won't even work. So we have to think about not having a be 0. But we can divide it off. A should be equal to 2 lots of 1 plus r. I'm pretty sure. From here then, what do we need to do? We are going to, what are we going to do? Plug this back into something to find a value for r. Yeah, let's plug it back into the first one. So doing that, what do we end up with? We'll have that 6 is equal to 2 lots of 1 plus r over 1 minus r. So we can divide that off, we'll have a 3 instead of a 2. So expanding some bits up, we'll have 3 minus 3r is equal to 1 plus r. Add those 3r's over, we get a 4r. Take that one away, we get a 2. Divide by the 4, we will have r as a half. So a then we can work out. If I add 1 to that half, I get 3.5 times by 2, I get 3. So that is my value to a and r. I then need to work out the sum of the squares. So thinking last time, looking at these other patterns, we had a, ar, ar squared, a squared, r squared, a squared, r4. So similar thing, we're going to have like a cubed plus a cubed, r cubed plus a cubed r to the 6, etc., etc. So our sum to infinity of that, the first term, a cubed, and we change by r cubed every time. So altogether, 3 cubed, 27, and then it's going to be 1 minus r cubed. R is a half, cube that is an 8. So altogether, it's going to be 7 over 8. And thinking about this then, it's going to be something over 7. Is that just the only one over 7? Yeah, 216 over 7. Yeah, 8 times 27 is 216. They'll often do that just to make your life a little bit easier. But I still would double check. But yeah, D is the right one. On to number 9 then. What's it saying? Find the complete set of values for the constant c for which the cubic equation has 3 distinct real solutions. Okay, so on these ones, what we want to do is differentiate. If we do that, we'll call it y dash. We will have 6x squared minus 6x minus 12 equals 0. So we can think about the turning points of that. Yeah, it doesn't equal 0, but like for the turning points and stuff. Divide by the 6, x squared minus x minus 2 equals 0. So we have x minus 2, x plus 1. So our solutions are minus 1 and 2. So when we go to draw this then, it's a positive cubic. So it does something like this, but not so pointy. Where this happens at minus 1 and this happens at 2. So we want to think about when do we have 3 distinct real solutions is whenever the horizontal axis, the x-axis, exists between those 2 points. It can't be either of those points, it has to be between them both. So that's our kind of leeway that we have. So let's work out what those points are. This one was 2. And when we plug in the value for 2, what do we get? We'll have 2 cubed is going to be 8, 16. Let's write this down. So we'll have 16. 2 squared is 4, times by 3 is 12. 2 times 12 is 24. That does a C. So that's going to be minus 36. So it's going to be C minus 20. And plugging in the 1, so C minus 20. Plugging in minus 1, we just alternate the things. So it's going to be minus 2, minus 3, plus 12, plus C. Minus 5 and a 12 makes a 7. So C plus 7. So this is good. So we're living in here somewhere. You can see that we have the ability to go as long as this thing is below our axis. So as long as this is negative. So we need to make sure that C minus 20 is negative and that we have C plus 7 positive. So we need to have C be less than 20 and C be bigger than minus 7, which you can write in one go. Minus 7 is less than C is less than 20, which is option B. Notice we didn't include any of them because you could never actually, like, we had 3 distinct solutions. If you equaled them, that'd be like a repeat one when it's not distinct. 9 for, well, B for 9. Yeah, lovely. Number 10 then. X and Y satisfy this thing and this thing. What's the greatest possible range of X and Y? So try to remember what this means. Like, this means difference. So this is the exact same thing as writing down that the difference between X and 2 is as big as 6. It's as big as it could be. So in that case, we know that X could be 8, yeah? Or it could go down to minus 4. Very similar. How far away are we from minus 2? We know that it's going to be 4 away. So minus 6 up to positive 2. So now what's the biggest value of X times Y? Ignoring any negatives. 8 and 6 makes 48. Simple. 10, E, yep, lovely, big tick, move on. Yeah, try and think like modulus. I don't think they explain it very well. Always think about it as being magnitude or like distance. It's the distance between the two things inside it if they're like when they're subtracted from each other. So difference between 2 and X. Difference between Y and minus 2. So thinking about that way around makes it much more easy to understand how they just like pop these bits, like how these bits pop out the other side. On to number 11 then. We got mx plus 5 is normal to the curve this at the point PQ. What's the value of P? Okie dokie. So let's do dy dx. That's going to give us minus 2x. So that's the tangent. So if you think about it, then what's the actual like gradient of the normal going to be? It's going to be minus 1 over that. So the negatives will cancel. We'll have 1 over 2x. That is our m whenever we put in any x coordinate for our graph. So this should be at the point PQ. So we can do this. We can plug in P and see that therefore Q, yeah, we can get rid of Q straight away. We'll get rid of P straight away. Let's get rid of Q straight away. So we know that Q is going to equal to 10 minus P squared. So now we have some expression for Q that we can use to get rid of it. That's good though, because now we can write down that y minus y1, i.e. Q, i.e. 10 minus P squared, is equal to m, 1 over 2x, where x is going to be P, lots of x minus P. This is our equation then. So we can slowly rearrange this thing. What we're going to get, we'll have a y, just expand these brackets first, y minus 10 plus P squared is equal to x on 2P minus 1/2. And what we should know is that this is the line mx plus 5. So doing that, what we can see is we rearrange everything. We'll have y is equal to x over 2p. We'll have a 10 minus 1/2. That's 19 on 2. Plus p squared. So we know this stuff is 5. So 19 on 2 plus p squared equals 5. That's not good. It's minus p squared. So doing that, we can add p squared over, take away that, and see that p squared should be 9 on 2, or i.e. p is going to be 3 over root 2, times on the bottom by root 2. We'll have a 3 root 2 on the top, a 2 on the bottom. So 3 root 2 on 2 is C, which is the correct answer. Lovely jubbly. On to number 12. It's this one, yeah. So we have some cubic. First thing to note, like we have positive, 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 negative. So this is a negative, sorry, not cubic, quartic. It's a negative one. So we go up, down, and down. And we're going to have some axes like this. We're told the intercepts, we have 0. We have, and then in order, P, Q, and R. P, Q, and R. And we've got lots of stuff about the integrals between different values. What things are we going to get? So what I'm going to do is I'm going to label, this can be A1, A2, and A3, which refer to the areas, not the values of the integrals, just the areas. So if we take the first one, what's that telling us? A1 minus A2 plus A3 equals 0. 0 to Q, we'll have A1 minus A2, and that will equal to minus 2. And then R to P, P to R will be A2 and A3. So negative A2 plus A3, and that's equal to minus 3. You can see then if we, so I'm going to slightly reorder these so they're all kind of lined up. Look at the first one, look at the last one. We know that when we have A3 and a minus A2, that should be minus 3. So effectively A1 minus 3 is 0. So A1 is going to be 3. We can use this then. We can see 3 minus something gives us minus 2. So A2 is going to be 5. And then we can have a look at A3 and know that when we do, on this one, let's do it. So we'll have 3 Minus 5 is minus 2. We have to add another 2 back on, don't we? The total area enclosed by it, 10. Yeah. Number 12. F, 10. Lovely. Yeah, you can kind of tell as soon as you get 8, like, you don't need to work that one out, do you? You know it's going to be at least 8. On to number 13 then. I think this was actually the easiest one I've seen in any TMUA, as long as you understand kind of the derivatives and stuff. So here we've got f dash. Like this is a graph of f dash. Where's the local minimum? Well, what does the minimum mean? F dash is 0, f double dash is positive. So it needs to be 0 and going up. Yeah, I don't think there's no, do you need to think about that? Not really, hopefully not anyway. If you're doing this paper, you shouldn't have to really think too much about that. Maybe just double check this way around, like is it C or A? But ideally that should be no thoughts, no thinking, move on and go. 14 then, line m equals 4x. 4x, mx plus 4 goes through these 2 points. What are the values of p? Okay, so let's plug them in. See what popped out the other side. We're going to have log 2 of p is equal to m times x, so i.e. 3m plus 4. And then we're also going to have a similar thing with this one, where we will have 4 is equal to m times this thing, and plus the 4. If we take that second equation, goodbye 4, goodbye 4, we can see therefore that we either need m equals 0, or we need to have log base 2 of p equal to 0. Well, this one on the right, that will tell us that p is 1. So that's kind of ruling out like some of these ones, yeah. Over here then, if m is 0, let's look on this side. This tells us that log base 2 of p is equal to 4, because the m is going to be 0, yeah. So looking at that, p is going to be 2 to the power 4 or 16. So 1 and 16 looks good to me. So should have pressed that one out, shouldn't we? Yeah, 1 and 16. Lovely jubbly. Is that correct? Number 14. 13 was C. I wanted C the other way. 13 C. Yep, lovely. 14 is B. Yep, beautiful. Find the sum of the real solutions of this equation. So let's just solve the equation first, yeah. What have we got? We got 3tx. But I'm actually going to write this as like this is root 3 squared, yeah, because you can see we're going to have lots of root 3s everywhere. So this thing, let's get that 4, rip it off there. So I need root 3 to the power 4. Well, root 3 is a half in a power already, so times that by 4 I get 2, so it's the same as 3 squared. So it should be 9 lots of root 3 to the x. This is going to be to the 2x. And then a plus 20 is still there, equals 0. Factorising this then, root 3 to the x. I'll have a minus 5 and a minus 4. So I can see I need to have that root 3 to the x is equal to 4 or 5. That looks good. And now then we want to kind of figure out what to do here. So this isn't looking so good nice, is it? Like with the roots. This is now where we go back to it being like 3 to the power of x over 2 is equal to 4 and 5. So x over 2 is equal to log base 3 of 4 and log base 3 of 5. So double those things, yeah, and then add them together. So 2 lots of log 3 4 plus log 3 5. If we add logs, it's the same as times in those bits together. So we'll get log 3 of 20. And we need 2 lots of that. So 2 log 3 of 20. Nice. Is that the right one? Answer is E. Answer is E. Lovely jubbly. Curve has this equation. Find the value for B that minimizes the distance between the origin and the stationary point of the curve. Okay, so let's find the stationary point. We'll complete the square. We'll have x plus a half of the B term, all squared. And then we'll take away that thing squared, so i.e. B squared on 4. And we still have the plus 2. So our turning point is going to be minus B on 2, i.e. the negative of that bit, and then the normal of that one. I will at the same time make this into one fraction. So over 4, this 2 would become an 8. So 8 minus b squared. Over 4, sorry, not over 8. And we could do something very similar where we make this into actually be over 4. So it's going to be 2 on the top and 4 on the bottom. So that's good. The reason we've done that now is if you're thinking about distance, if I just scaled everything by 4, it makes no difference where the biggest and smallest is. Does that make sense? It's just stretching everything, but you're stretching everything the same. So we can now just find the like exactly the same. This is like equivalent to just not having the unfold there. So what's the distance going to be? The first thing will be 2b all squared, so 4b squared. And here we're going to have this thing squared, the numerator there squared. So 64 minus 16b squared plus b to the 4. That's the distance squared. So we could think about doing the square root of that. But again, same idea. The smallest value of something is the same if I square it or not. This distance is always positive, so we can never have negative ones in there. So let's find the turning point of this basically. Let's do dd, db. I could collect, I could just collect, I suppose, can I first? I got b to the 4 minus 12b squared plus 64. Now if we differentiate, we get 4b cubed minus 24b. 64 will go away, won't it? So we can factorize that, take a 4b out the front. And what I'm left with, b squared minus 6. So you can see this is going to happen either when b is 0 or root 6. Plus or minus root 6, I suppose. I think the question does say, yeah, b's got to be positive. Could be 0. So we should really go through and check which one's going to be the smallest in that case. We could, however, just differentiate again. So if we look at d2b, db squared, we get 12b squared minus 24. And what you can see is that if b is 0, this is negative, yeah? So that's going to be the maximum, but we want a minimum. So we need to use the plus or minus root 6, but we couldn't have a negative one, so it is root 6. 16, is that all good? F, yep, lovely jubbly. On to 17 then. We've got 2 sets of data. Mean for the first set's 15 and for the second is 20. One piece of data is from the first set is exchanged with the pieces of data from, with one of the pieces from the second set. As a result, the mean of the first set increases from 15 to 16, and the second set from 20 to 17. What's the mean made by combining all the data? Okay, so we can write some stuff about the first one then. We know the mean is 15. So let's say that there's n of them, and there can be m of the other one. So what we can say is that 15 times by n is the total. That can be the total of like total 1. And the second one then will have the same thing, but total 2 will be equal to 20 times by m. They then do like the rearrangements, don't they? But we can do similar things. We're going to have like total 3 will now be 16n, and total 4 will be 17m. We still have m's and n's because they've just swapped one piece of data each. So the amount of them that they have is still the same, i.e. n or m. Why we've done this, these are the totals, yeah? That's the total before the swap, this is the total after the swap. They must be the same. I haven't gained anything new, I've not removed any data, we have the same amount of data. So we can say the original values, the original totals, so the 15n plus 20m must be the same as 16 and 17. So we can subtract some bits across, we'll have 3m is equal to n. This is good. From here then, what we can do is take any one of these equations. So let's look at this one, and I'll plug in instead of the n, the 3m. So we can see the total, like just the full, yeah, this is like full total, isn't it? So full total then will be 15 times 3, 45, plus a 20 is 65. Lots of m. And from there, what can we do? We can think about the fact that how many pieces there are in total. Well, there's 3m, well, there's n and m in there. And we know that the n we can replace with 3m. So altogether, like the actual count is going to be 4 lots of m. So the mean then that we can think of, that's not very good for mean, total mean, is going to be 65 on 4. 64 would be 16, so 16 and 1/4. That's all good. On to 18 then. Smallest possible value of a for which the line x equals a is the line of symmetry of this graph. So notice it's a vertical line. So how do we get a line of symmetry? Well, the sine graph itself is going to be doing stuff like this, isn't it? Anytime that we have like the peaks, they act as a line of symmetry, because everything you do to the right is the same as what you do to the left. So we're basically asking the question, when does this, let's just leave it there, when does this equal plus or minus 1? So we have sine 2x minus 4 pi on 3 is equal to plus or minus 1. So thinking about that then, 2x minus the 4 pi on 3. The plus or minus 1 will happen whenever we have like pi on 2, or 3 pi on 2, or 5 pi on 2, etc., etc. Any odd amount of pi's on 2. So what we can do is we can always add basically like 1 pi as we go through. Any additional 180 or pi will be good for us. So this is good. We want to rearrange then for the x effectively. What I'm going to do is try and write everything over 6. So it's like the common denominator that we have, or the lowest common denominator. So doing that, we'll have 8 pi on 6 is equal to 3 pi on 2, 3 pi on 6 plus 6n pi on 6. So that's good, still with the 2x. So now we can add everything over. We'll have 8 plus 3 is 11. And then we'll add on still the 6n pi on 6. And then divide them by 2. So we'll have 11 pi plus 6n pi all over 12. We want the smallest possible. So you can see here that we can plug in either n as 0 would be fine, give us 11 over 12, which is d. So that's an answer, but it's not the smallest. The next one then, let's do minus 1. Can we go down? Yeah, we'll get 5 over 12, which is an answer. If we did any more than minus 1, let's say we did minus 2, we'd end up negative. So too big, well, too small, I suppose. So in this case, we need to be doing n is minus 1, give us 5 on the top, and having 5 pi altogether. 18 is B. Lovely. 19 then. Triangle ABC is to be drawn with AB is 10, BC is 7, and the angle equal to theta. And notice that as angle A, it's not the one in between the two sides here. Of the two possible triangles that could be drawn, the large triangle has 3 times the area of the smaller one. What's the value of cos? Okay, well, let's get our 10 along here, and our angle can go up there somewhere. So we've got this sort of idea. And the line BC then, so let's just draw what we have. This is angle A, this is going to be B. C, therefore, is going to be somewhere along this line, but we don't know where it is. But we can basically guess and say, okay, well, it could be there. It could be there. That's not very good. What? That's not. There we go. Something like that. Let's call this C1 and this C2. So we've got some information there. We know the line lengths there are 7 as well, just to fill those in. I think that's all we need. So one thing we can do is get the cosine rule for both of them. But before we do that, it's quite nice to actually have like ways to express these lengths. So I'm going to call this one x. And let's just think quickly about like, the only things we know, the larger one is 3 times bigger than the smaller one. How do we work out the area of a triangle? You do half AB sine C. So if we think about like from this angle, this and this don't change. The only thing that does change, therefore, in the form of the area is this length. So if it becomes 3 times larger, A to C2 must be 3 times larger than A to C1. So if we call that x, we know this bit is going to be 2x up there. and i.e. the whole thing is 3x from there to there. So that's all good. Let's do the cosine rule then, and we'll do that where we know about the angle A. So we'll have the 7 squared is equal to a squared, i.e. 10 squared, plus I'll do the small one first, plus x squared, minus 2 times a times b, so 20x cos theta. The big triangle then starts off the same. X there is now going to be 3x, so we're going to have 9x squared. And this is a very similar thing. It's going to be just times by 3. So from here, let's do a subtraction. We'll do bottom take top. But we'll just, bottom take top's okay. So we'll have 8x squared left there. So you can see that goes. And this one, take away that one, is minus 40. And they should all equal to 0. So either x could be 0, but that's not very exciting, is it? Or what we can have is that x is going to equal to 5 cos theta. So that's one of the bits done. We're kind of halfway there. And from here then, we'll take this and sub it back in to either one of these, but we'll do it the easiest one. So doing that, what we're going to get is that 7 squared is equal to 10 squared, plus the x squared, i.e. 25 cos squared. Take away 20 times this x. 20 times 5 is 100. Cos times cos is cos squared. Collect some bits then. This will make a minus 75. So I'll add that over to be positive 75 cos squared. And 100 take 49 is 51. So dividing that across, we'll have 17 on 25. And then square root and all that stuff. Root 17 on 5, not 2. Is that one of the answers? It is root 17 on 5. Lovely jubbly. Last one then in the paper. Oh yeah, this is quite a sneaky one. This is one, if you know it, it's quite straightforward. If you don't know it, it's not too hard to figure out, to be honest. One thing they say in the book is like just to write it again and then you add them up and do stuff. But I think the best way is just think about like sine and cos are the same shape but in reverse, aren't they? So what you have is that sine of something is equal to cos of 90 minus that thing. So effectively, this sine of 90 is cos of 0. It's cos squared of 0. And then we have cos squared of 1. And then we have cos squared of 2, etc., etc. So we're able to go through and pair up terms in this sequence, where like the first pairs with the last, the second pairs with the second last, third with the third last, etc., etc. How many times can we do that? Well, all the way through until 45 won't have a pair. So we will have made 45 full pairs, i.e. we're going to have like sine squared of 0 plus cos squared of 0 plus sine squared of 1 plus cos squared of 1 all the way through. Let's do it this way around. All the way through until we get down to sine squared of 44 will be fine, and of 44, and that one is fine. But then we just have left over sine squared of 45. All of these are just 1 because it's like cos squared plus sine squared is 1. And then the last one we have at the end, what is sine of 45? Root 2 on 2. Squaring that, it's a half. So we have 45 ones and a half gives us 45 and a half. This is quite a common thing though, do you know what I mean? It's whatever you, it's basically whatever you have in the middle. Here we had 90 of them. 91 of them, it's just half of that. Nice way to think about it. So what they do is write down like the whole thing again in reverse. They like would pair this up, like have another one, 0, 1, 2, etc. And then swap them over for causes, and you see that you have all of them make a 1, you have 91 of them, and then you divide by 2. Both ways work exactly the same, or give you the same answer. Lovely jubbly, hope that's all good. Any questions, leave it down below. If not, thanks for watching, and I shall see you next time.